Hi, my name is Olivia. I'm a second-year PhD student in theoretical neutrino physics at Northwestern University, and today I'll be talking about an ongoing study involving time invariance violation and matter-based neutrino oscillations. To begin, I'll very quickly show the outline of my talk today, and then just very also quickly note that in particular, the study focuses on understanding how much time invariance violation, if at all, can be observed in neutrino oscillations and to what extent we can differentiate these observations from those just brought on by neutrino matter potential effects. So getting right into it, if we follow that CPT is a fundamental symmetry, but also recalling too that charge parity transforms alone are violated in the weak sector, it follows that time inversal transforms also alone should be violated in the weak sector in order to preserve the overall symmetry. Now, neutrino physics is already a well-motivated probe for studying CP violation, so it makes sense to look at things from a time reversal point of view as well. The main reason is new physics. New physics may not impact both CP and time reversal in the same way. On a more practical side of things, normally when we look into studies involving matter effects for neutrino oscillations, we tend to look at the CP conjugate channels. The reason being is that they're often much more accessible to experiments. However, they do come with non-trivial matter effects. This is where looking into time invariance comes in handy. So yes, while they can be more difficult to handle experimentally, they do give a clearer way to differentiate between what we call the true time invariance violation, or checking to see if the matter effects themselves are masquerading as such. In other words, understanding the difference between intrinsic versus induced time invariance violation. Now, just so that we're all on the same page, I'll very quickly review the three flavor neutrino oscillations in the case for charge current matter effects, given the typical Hamiltonian shown here, where I note the matter effects themselves are presented in the usual way where we take this to be a constant. Then, since we do care about looking into the matter effects explicitly, if we follow this prescription of writing down the probabilities, we see things written down directly in terms of the unitary transforms. And in particular, we see exactly where the matter effects have the role. In terms of the context for this talk, let's consider some hypothetical baseline of an experiment, say L, and we'll break it up into two steps, L1 and L2, where each has their own evolution and each has their own matter potential A1, A2 respectively. Looks something like this as an example. Now, if we had just a single constant matter potential, you could think down at the fundamental level, your A in terms of your baseline L could look something a lot like this, versus for the two-step, you can imagine something that looks more like that. In principle, though, you could have an n-step matter potential that is useful to sort of approximate more complex forms. And the key takeaway is that at each step in the multi-step potential, these are constant. So we say it's a piecewise constant matter potential. The reason why I spent a little bit of time reviewing and describing this in detail is that understanding things at such a fundamental level gives better intuition for why, in the course of the study, we defined two different time invariance measures. First one, proper time invariance, or the true time invariance. This one, it's not such a good observable, but it's certainly no harder to calculate than the CP conjugate channels. The key thing is to talk about things in the proper sense. We're essentially comparing probabilities with the final states interchanged, as well as swapping the detector with the source. Now, in terms of the case for the two-step potentials, essentially you can imagine maybe an increasing potential or a decreasing potential. And what we're comparing in the proper sense is what's in these two boxes here. This is in contrast, as opposed to looking into the proper time invariance, where essentially for the same two-step case, we pick one potential, maybe it's the increasing variety, and this is what we're comparing. So essentially we're comparing only the probabilities with just the final states interchanged. Might be asking yourself, well, why do we care about having these two different measures? Well, the improper version is the one that is observable in experiments. Also, understanding these two different measures, it helps us have a better picture on the relationship between these measures and the characteristics of the matter potentials themselves. And for the purposes of the study, we looked at two types of potentials. We looked at symmetric and non-symmetric. In particular, a symmetric case was when we're looking at vacuum probabilities or single matter potentials. On top of that, and yes, the vacuum potential is zero, so by construction, it is technically symmetric. And then in the non-symmetric case, this is where the piecewise matter potentials come in. And then just noting that in the course of the study, all the parameters that we'll be using have been drawn from the NewFit 2022, except for CP. So from that, now moving on to the results part of my talk, I'll very quickly note that these results are preliminary and that the first set I'll be showing today are done with hypothetical or fictitious matter effects. And this is basically just to get an overall general sense of intrinsic versus induced time invariance violation on scales where oscillation differences tend to be larger. And then the final part of this talk will look at some more realistic projections for DUNE and T2K. Now, jumping right into it, for the symmetric matter case, and note that I'm considering delta CP equals 0 here. So in this case, also note that the two channels, nu mu to nu e and nu e to nu mu, are the same, whether we are looking at the matter probabilities or the vacuum probabilities. So for the vacuum, they're here, matter, they're here. This is in contrast to when we're considering the case when delta CP is maybe pi over 2. In this case, all the probabilities are different. Now we're packaging this information in this by probability plot where the dotted line is just a time conserving line and the energy I took is just a point where the probabilities were at a good place to compare against. Key takeaway is that symmetric potentials cannot induce time violation. However, if there is intrinsic time non-conservation by having a delta CP maybe being pi over 2, then the matter potential just changes the degree of the observed effects. Note, and nowhere in the symmetric explanation did I quantify proper versus improper comparisons. There's a reason. When the potential is symmetric, these two are the same. Why? Well, if you recall, the difference between the two measures was that you would get different results exchanging the source of the detector. At the fundamental level, this is comparing, say, an increasing versus a decreasing potential, not when it's just straight constant. So the single constant matter potential is by construction symmetric. And that's why these comparisons are the same. Moving on now to the non-symmetric case, I'm going back to when delta Cp is equal to 0. In this case, you'll notice the hypotheticalness of the chosen matter potentials is more clearly seen. So even though the first value for the matter potential, or the first step, is just slightly less dense on the crust of the Earth, the other one is relatively more dense. And in such an extreme, or as much as it can be, you'll notice that the changes in the probabilities relative to each other is actually quite small. So this is the motivation for why looking at the fictitious case first to establish the trends was important for this study. The key thing to note is in the non-symmetric case, these effects appear to be pairwise degenerate. This means that proper time invariance channels hold. The improper ones can be different, and in this case, they are. Furthermore, another way to rephrase that is there is no intrinsic time invariance violation, but there is matter-induced time invariance violation. To be clear, for the proper comparisons, we're looking at a comparison like between those two, and which are the same, or those two which are the same, versus these two which are different, and that's in the improper comparison for those two, also improper and different in this case. Also looking at the non-symmetric potential with delta Cp as pi over 2, you'll note that very much the same conclusion is drawn as from the symmetric case. There is this intrinsic T non-conservation. They're all different. And the matter potential just changes the overall magnitude of the oscillations. Now moving on to a little bit on the preliminary results following my applications to long baseline experiments. The first is looking at symmetric potentials at DUNE. I'll note that here the constant matter is precisely corresponding to the one for the density of the Earth's crust. Also, which was just not too far off a fictitious single constant matter case, actually. And the energy I chose is the same from the fictitious case, so that we're truly comparing like quantities. So really the only thing that's changing here is the baseline. It's smaller. And just from this preliminary case, looking at the bi-probabilities, both for nu e and nu mu, and nu mu and nu tau, we see that generally the conclusions for the symmetric potential not having any time violation hold, but just that the overall differences in the probabilities are smaller, which is to be expected from a smaller baseline. So that corresponds to just the sort of the smaller area enclosed by the ellipse. And another thing to note that as these effects, if they can be seen at all, would be quite small. They are in the right probability range of some of the projections for the CP conjugate channel. So it's definitely in the realm of probabilities that DUNE would be able to probe. And very much the same story is true when we look at the case for the symmetric potential at T2K, just again changing the baseline, so it's smaller effect, if at all. But the overall conclusion, at least in this preliminary case for the symmetric potential, holds. Finally, I will finish by just noting it's a little bit of some future studies that I hope to do in the near term. The first is diving a little bit more into some interesting cases where maybe the matter-induced timing violation occurs, or some more realistic models that are non-symmetric. Also, some next steps will include the non-standard interactions, specifically for DUNE. And this will be a follow-up to previous work on the same topic shown here for non-standard interactions. And with that, I'll leave you with just my takeaways from the study I discussed here today, and that this is just an ongoing work into understanding more about time invariance violation and how it plays with the simple neutrino matter potential models, noting that there are different results depending on whether the potentials are symmetric or non-symmetric, and that if the effects are visible at some of the long baseline experiments, it would be relatively small, at least with these preliminary results, and that there are many future studies that can be done as follow-up to what I've shown here today. There's a lot of exciting information in the future on this material. And with that, thank you.